Okay, so do we have any homework questions?
Gonna give us a hint on the last two MATLAB.
Oh, okay. Oh, so ones you asked me about earlier. Yeah, okay, yeah.
Well, that's where we're all at.
Okay. Let's see.
Not to snitch.
Okay. All right. So if we can talk about for that problem, for those two problems. Okay, I'll have this in front of me. All right, so this is 451 and 453. Okay, so okay, similar but still slightly different tips for two. Okay, now you'll notice that so both algorithms for least squares linear constraints require QR factorization, but the QR factorizations they require are different. 4.5.1 requires the thin QR factorization, and I don't recall if I mentioned this before, but certainly we're mentioning now, because normally if you do something like this, QR is equal to QR of A, the MATLAB standard function for computing QR factorization. But that, if I were to close the parentheses, does the, because there's a reason why I haven't, that gives the full QR factorization, where Q is a square matrix, M by M, and R is the same size as A, and may have 0 rows to it. But you don't want that. You do want it for the other problem. But here you want fit QR where Q is the same size as A, and R is a square matrix. So for that, you do A, comma 0. And that gives you the type of QR factorization you want for this problem. It doesn't hurt to have a rest, but you'd be tossing stuff out. Okay. Now, the other thing I want to point out about this problem, and which actually might cover everything. Okay, that most of the steps in this algorithm that's given are of this form. Solve some equation where you'll always have a matrix, and then either a matrix or a vector that's multiplying it, and then some right-hand side, which again could be either a vector or a matrix, doesn't matter. Okay. And you're asked to solve that for x. Yeah, you have 5 tasks in this problem that fit this form. So what you do for that is that's what backslash is for, because this actually computes A inverse B. But it's important that the slash go in that direction. Whereas if you did this, that does A B inverse, which you don't want here. But I want to make you aware of both operators anyway, in case the other one might be useful. All right. One thing I want to make you aware of is because it happens at least once in this problem, if B is an expression of some kind, like maybe it's some things added together or multiplied together, you probably want to in that case you want to put parentheses around it to make sure that it fully evaluates this first, then carries out the backslash operation. Any questions about that? Okay. All right. Let's see. Yeah, I think that should get you guys through that problem. But I have a little more to say about the other one. So for this problem, QR factorization. So you can go ahead and use MATLAB's QR function, but without the 0. So it's default usage. And you have, but the thing is, Q, all right, so A is equal to QR, and I've heard this before, where Q breaks down into 2 parts. And because we need to refer to Q1 and Q2 and also to R1. So in the case of, to extract Q1 and Q2, you need to be able to take selected columns from a matrix, whereas for R1, you need to be able to extract certain rows. Now, as far as dimensions go, oh wait, in this problem it's C, not A. That gets QR factorized. So C is given to be n by P. So Q is n by n, R is n by P. So Q1 is has P columns, and then Q2 has n minus P. And then the top P rows of R are R1. Okay, so so for example, Q1, so you're taking columns from Q. And I use a general notation here. Start column, end column. Because you're specifying a range of columns that you want to take. So you would do that for Q1 and also for Q2. Now technically here, for the rows, you would also, which in this case would be 1 to n, but if you're going to take all rows or all columns, you just use a colon by itself. And MATLAB understands that to mean all indices. So for Q1, so starting column would be 1, and then the ending column would be P. And then you'd be taking the rest of the columns in the same way. So Q2 would be a similar situation. Now, whenever you're extracting rows or columns, and you're specifying a range like this, you can use end, and that is understood to refer to whatever is the last index. Okay. Similar thing for R to get R1, but then you put the range here. Specify which rows you want, and then comma, colon. So your range of columns, your range of rows, comma, colon, to take all columns. In this case, you'd want 1 through P. All right, so, well, I just said it, so I'll fill it in there. Now, since the function is only being passed A, B, C, and D, you need the sizes of these matrices as variables. So that's something you need to be aware of. So to get the dimensions of a matrix, So generic usage. Like you can do that. If A is an m by n matrix, and that'll get you both the number of rows and the number of columns. Or if you only wanted the number, you can do size 8, 1 rows and columns, 2. So that you'd be performing all the time. Love how USM's internet is. Well, okay.
I keep writing SINZE because I've been writing sign all the last.
So, questions about these problems? Or anything else in the homework? What? Oh, okay. Seriously though.
I think those were
Oh, okay. So everything else was squared away. Or...
putting all our brains together.
Okay. Oh, that's good. Yeah. I think like combined brain power works. So, yeah. Okay. All right. So during the hour and 9 minutes that I have left, we'll see if I can get through 2.5 pages of notes. What? But someone tells me I won't be able to finish early. But I don't want to tease about something like that and have it not happen. I feel guilty. Okay. Now, so this is a follow-up to the last topic I covered, which was almost 2 weeks ago. So can't blame you if you've all forgotten. The method of steepest descent. So today's topic will be Lanczos Iteration. So section 522. Yes. And I guess technically even I don't pronounce it correctly because when I showed up for my interview here in 2009, one of the faculty members who fancied himself an expert on pronunciation of all languages corrected me. So, well, talk about a guy who, when he visited Lake Pontchartrain, thought that he would get somewhere by giving it the proper French pronunciation, Pontchartrain, and actually thought that people would understand him. Yeah. So, yeah. But I know that Lanczos is close to the correct pronunciation, so we're going with that. And certainly this will be a topic of great importance to anyone who does research with me in anything closely related to KSS methods. So, all right. So, so the problem with we're solving this problem, AX equals B, where A is symmetric, positive, definite. And we're looking at iterative method instead of using a direct method like Cholesky factorization. Now, we have this method already that I covered before the break. Method of steepest descent. each iteration of steepest descent is guaranteed to make at least some progress towards the solution of x. The problem is with steepest descent that it's very easy to come up with an example where it makes very little progress from one step to the next. And I'll just summarize the defects. So why steepest descent can converge very slowly is each residual, and refresh your memory, and I may have indexed it differently for steepest descent, but this is a notation I'll be using today. So I'm just going to go with that. So, because you want this residual to eventually become 0. So but until it is, each residual is orthogonal only to the previous one. As opposed to, I should say, I'll emphasize previous one residual, not all previous residuals. Because having your current residual, which is your search direction for steepest descent, be orthogonal to a previous direction, that makes perfect sense. That you want to cover new ground each iteration. The problem is, steepest descent has no memory, if you will. That it may cover new ground compared to the previous iteration, but it's maybe covering the same old ground as 2 iterations ago, or 3 or more. So that's what I mean by steepest descent not having any memory. So it only is only independent of whatever happened 1 iteration ago. So that's why in a case where a 2x2 matrix that should be able to solve very quickly, it has a zigzagging effect. That each direction is perpendicular to the previous one, and then it's parallel to the one before that, and thus the zigzag. So we want a method that has some kind of memory where we can guarantee that each residual will be orthogonal to all previous residuals. So enforcing that in the design of a method from the beginning is going to lead to this Lanczos iteration. And then that will be a step forward. And then improving on that, which I plan to do on Wednesday, leads to the widely known conjugate gradient method. Okay, so all right. So first I need to set some notation. So I need to ensure orthogonal residuals, as in each residual is orthogonal to all of the previous ones. I'm going to specify a form for each iterate. So xk is our guess our kth guess at the solution to ax equals b. So it's going to be equal to an initial guess. That's of our choosing, and by default we could always choose 0 for that. Plus some matrix qk, so this is going to be n by k times the vector yk. Now, I'm also going to specify that the matrix qk has orthonormal columns. Okay. So, in other words, I'm going to make sure that my residuals that I get from one iteration to the next are going to be in these directions, the columns of QK. Because to be orthonormal, these vectors have to be perpendicular to one another, and they also have to be unit vectors, magnitude 1. So if I can make sure that the residuals are parallel to these columns of QK, that would guarantee each residual is orthogonal to all previous residuals. And the role of a vector yk is it's just a vector of coefficients, because qk yk, if I write out both, so these are the columns of qk. And then I'll write out the elements of yk. These are just coefficients in a linear combination of these columns. So if I wrote out the matrix vector product, it would be, God, this chalk is driving me nuts. y1k q1 plus y2k q2 plus ykk qk. So all I'm saying by specifying a solution as this form is that it's equal to the initial guess plus some linear combination of these orthonormal vectors. So in other words, this vector here is in the span of is in the span of these columns. All right. Now, so now that I have this form for my solution, I can use that to get an idea of what the residual looks like. So I'll define rk plus 1 to be b minus a xk. So now what I can do is I'm going to take this expression for xk, substitute it in here. So I just realized I made a mess of my board, but okay. So that's b minus a x naught plus qk yk. So now if I group these differently, so b minus a x naught minus a qk yk. But this vector here, b minus ax naught, that's my first residual. So that's r1 minus a qk yk. Now, what I'm going to do is I want the columns of this matrix to be parallel to my residuals. Well, there's my first residual, R1. So I'm going to use that to get the first column of QK. In other words, the vector Q1. That's my first residual. In other words, I'm going to say, I'm going to let Q1, which is the same thing as QKE1, first column of QK. Okay. And that will be equal to so I can find that to be R1 normalized. So in other words, I'm dividing by the 2 norm. Or put another way, R1 is equal to beta naught Q1, where beta naught is the norm, is the 2 norm of R1. And I'm introducing this notation because I'm going to have these a sequence of coefficients, these betas. So that's going to start it off. Okay, so now because my first residual, R1, that's something I can compute immediately because X naught is my chosen initial guess. So I just plug that in here, I get some vector R1, I divide by its norm, and bam, I have the first column of my QK. Of course, that tells me nothing about how to get the other Qs, the subsequent columns. But I'm coming to that. Okay. So now I have, so let me write out what I have now. So that means that each residual, RK plus 1, is equal to beta naught QK E1, which is the same as Q1, minus A QKYK. All right. Now, what that means is each one of this residual number K plus 1, belongs to the span of Q1, because that's what this is, and then A times the columns of QK. So I have AQ1, AQ2, etc., up to AQK. Now keep in mind, I only have Q1. I don't know what Q2 is yet, or any subsequent Q. But I'm trying to find a good choice for it, for these things. All right. So, but look at my first two vectors, though. I have Q1, and then I have AQ1. Now, but this span is the same as this span. I can take any vectors that are parallel to these, and it's still the same span. So that's the same as R1, because R1 and Q1 are parallel. AR1, and then I have these others I still don't know yet. Okay. So look at the first two vectors. That's my initial residual. Here's A times that residual, and then whatever comes after that. Now, so since I'm taking columns of my Q and multiplying them by A, it makes sense to make each of these columns of QK some polynomial of A times R1. So, okay. What's the best way to explain this? Like, if I have R1 and AR1 here, why not make this like A squared R1, A cubed R1, and so forth? So, polynomials of A of increasing degree times R1. So, so numbers, what I'm going to do is, okay, need more board space for this. I was trying to stay away from clear zone altogether. Just easier. So what I'm doing here is I'm making a conscious choice here as to what my Q vectors are going to be, in the hope it leads to an efficient method. It's not the only choice I can make, certainly, but so my choice is, I'm going to choose the columns of QK to form an orthonormal basis, because they're already orthonormal. I'm stipulating that. So I'm going to work with this subspace that's spanned by first two vectors I already have there, R1, AR1. So now I'll just continue. A squared R1, a cubed R1, and so forth. And I need K vectors altogether. So that would be, all right, so A to the K minus 1 R1. And I'm going to give a shorthand for this. So my fancy K, R1, A, and then ordinary K specifying a dimension.
Is that a comma in between the A and the ordinary K?
Yes.
Okay.
Yeah, comma here, comma here. Okay. Now, so this is a subspace of Rn. And it's called a Kree Law of Subspace. Okay. Krylov, not Krylov. I pronounced it Krylov for many years before I finally got set straight. And I guess many people in the field still pronounce it like Krylov because maybe think of like a spray paint, Krylon or something. So, yeah. So, but there's so many iterative methods for AX equals B that rely on Kree Law of Subspaces. Very, very incredibly useful. And they're also a basis for a major part of my research program, Kree Law of Subspace spectral methods. Yeah. So, okay. So in other words, we're looking at vectors that are obtained by applying some polynomial of A to my initial residual R1. They're all going to have that form. Okay. So in other words, each vector Qj is equal to some polynomial of A times R1. So Pj minus 1 is a polynomial of degree J minus 1. So the degree is the index. And I can already tell you what the first polynomial is. So P0, that's degree 0. It's a constant. And all it is 1 over beta 0. That's what we did over here. To get Q1 is R1 divided by beta naught. Oh, whoops. Sorry to whoever needs to watch. So, sorry, Bailey. Okay. Now, all right, and I'll have a lot more to say about these polynomials in a bit. But first, I want to use the fact that I want all the residuals to be orthogonal to each other. That will actually help me figure out this vector, this vector right here, this yk. Because that tells me how to combine all these vectors to get my solution. Okay. So, right now I still have all these unknowns. I don't know what I have a form for the q's, but I don't know how to get these polynomials yet. I don't know what yk is, but I'm about to figure that out. Okay. So to require each residual to be orthogonal or perpendicular to all previous residuals. Okay. Now I need a way of describing that condition as an equation. So I want QK transpose RK plus 1 to be equal to 0. Because remember, my columns of my QK, those point in the directions of residuals. They just all have magnitude 1. So that's the same as saying QI transpose RK plus 1 is equal to 0. I equals 1 up to K. All right. Yeah.
Okay, and I could be making this up. Because it's perpendicular, that means that it's orthogonal?
They mean the same thing.
Okay, just making sure.
Yeah. Yeah, I guess we first say orthogonal when we're talking about vectors in more general spaces, because perpendicular is only like for n-dimensional Euclidean space. But yeah. But that's actually the space that we're in, so I can use either word today. Okay, so I'm going to enforce that condition. So I need to fill in what RK plus 1 is, and I had it written down before, but okay, so RK plus 1 is equal to B minus AXK. Actually, this is a 0 vector because I'm taking K inner products and requiring them all to be 0. So now if I fill in what this is, I had that written down before. QK transpose R1 minus A QKYK must equal 0. All right. Now, R1, though, R1 is parallel to Q1, so I'm going to fill that in here. QK transpose beta naught R1, beta naught Q1 minus AQKYK, 0. All right. Now, well, beta naught's a constant. I can pull that out. QK transpose Q1 minus QK transpose AQK YK 0. Okay. Now, but Q1 is the first column of capital QK. So I'll fill that in. So beta naught, I already pulled out. Okay, so QK transpose QKE1. So that's Q1. Minus TK YK is equal to 0, where TK I'll define to be the expression I have down there, QK transpose AQK. Now, can anyone tell me what simplification can be made in that last equation?
Which last, like the last term or the last thing?
Actually, it's this term.
The identity.
Yeah. QK transpose QK is identity because QK has orthonormal columns. So I'll rearrange here. I get TK YK is equal to beta naught E1, first column of identity. Okay. So now I have a system of equations for yk.
Pause. What?
Yeah. What?
Okay, I said identity. Re-say everything after that.
Okay. So that goes away. I just have beta naught E1.
Oh, okay.
And then I move this to the other side.
That's what I needed.
Okay.
I was like, what happened to everything? Why am I starting with
Okay.
Good.
All right. So once I have TK, which I'll explain how to get that, I can solve the system to get YK. Now, TK, what do we know about it? Very little so far. It's K by K, and it is symmetric positive definite because A is. So if you have a matrix like this, a matrix like A, and you multiply it in the left and the right by like something on the right and then it's transposed on the left, and QK has linearly independent columns. So whenever you do that, it's called like a conjugacy transformation. If this is SPD, so is this matrix too. So we can solve that using like Cholesky's factorization or whatever. So because the idea is A may be a large matrix, but TK should be a small one because this is the iterative method. Now it's going to grow with the number of. It won't need too many iterations. That's the point. We're trying to speed things up and take far fewer than n iterations, preferably. Okay, so if we can just figure out what our Q's are, then we know how to get this. So that's no longer an issue. So and that will help ensure all residuals, each residuals are orthogonal to all previous ones. So that was the requirement going in. So now we know how to satisfy that. Okay. Well, I said I had 2.5 pages of notes. That finished off 1 page right there. All right. Now, so I mentioned before, we have a form for these Qs. So each Qj has this form. It's some polynomial times R1. Now, I should point out there's a mistake in the book. This is from page 178. So in the book, I have B here, which is not general enough. It would only be B if your initial guess was 0, which I think when I was first running these notes, I just made that assumption, but then I got rid of it. So there's a few places on this page where I have B. It has to be R1. So, okay, now I want Qi transpose Qj to be equal to 0 if I is not equal to j, and 1 if I equals j. So what I'm going to do is I'm going to fill in what this means in terms of these p's. So I have R1 transpose Pi minus 1 of A, Pj minus 1 of A times R1 to be equal to 1 or 0. Okay. Now, see while you're paying attention. I had Qi transpose. This is part of Qi transpose. How come I did not have to put a transpose here? How come I did not have to put a transpose here? Because this is part of Qi, which got transposed. So I do need a transpose here. But how come I didn't have to put one here? What do we know about A? Symmetric, positive definite. So the symmetry of A meant I did not need to do that.
Is that a vector above the R? It's not a negative.
It's a vector symbol. Yeah. All right. So what I can say is these polynomials, P0, P1 up to pk, let's say. Well, okay, I'll leave this k. Probably should be k minus 1, but it doesn't really matter. Are orthogonal. Actually, more than orthogonal. They are orthonormal polynomials. I have to be more careful about this because when you say orthogonal polynomials, often the orthonormal is implied, but not necessarily. It depends on what book you're looking at. So, but I can definitely say they're orthonormal polynomials with respect to this inner product. So now I'm talking about, instead of an inner product of vectors, it's an inner product of functions. In this case, polynomials. So this inner product is defined to be R1 transpose F of A, G of A, R1. So, because you can define orthogonality with respect to any inner product that has the valid properties of inner product. So this is the inner product I'm using in this case. So I'm saying that these p's are orthogonal or orthonormal polynomials with respect to this inner product. So I'm going to use that to figure out what the p's are, and once I know that, I'll know what my q's are. And then I'll have everything. Okay. Now, so dealing with orthogonal polynomials. Or really generating orthogonal polynomials. Now we could use something that I actually covered earlier for least squares problems. So, because we know the first one, P0. I wrote that down earlier. Oh, yes, I erased it. We can use Graham-Schmidt's orthogonalization. Kind of like for the QR factorization. So we're given the first one, P0 of lambda. I can use lambda as my variable, is 1 over beta naught. So given the first one, we're now going to I'm going to show you how to generate all others. Okay, so, yep, I'm probably going to fall behind, but whatever. So what I do is, Graham-Schmidt would give us this. I can define this polynomial, Gj. Gj is meant to be orthogonal to all previous p's, but not normalized. So what I do is, I take my last polynomial and multiply it by lambda. Why? To increase the degree. So this has degree j, and therefore so does this. Then I need to subtract terms off of it to make this Gj orthogonal to all previous p's. So and to do that, I need these inner products. Okay, so I have so this is how I make each new polynomial Gj orthogonal to all the previous ones, all previous p's. So let me write that down. So Gj inner product with pi is 0. for all smaller indices. Okay. And the way you can show this is if I take the inner product of both sides of this with pi, that's how I get these coefficients. Or actually, I can take the inner product of this with pi, and I would get 0. So it would confirm your orthogonality. Okay. Now, then to get my next p, I need to normalize. Now this is the norm of Gj. So that's what I'm doing. I'm dividing by the norm to make it have unit length or unit magnitude. Okay. So now all the p's are orthonormal to each other. Okay. The problem is this looks really cumbersome because it's saying that each new polynomial depends on all previous polynomials. But for anyone who's done Math 685 homework for me, they've seen that that's not true. But it's only a few people in this room. But I'm going to show you why. It turns out these coefficients, these inner products here, most of them are 0. And I'll show you why. So this inner product here, pi lambda p j minus 1. I can rewrite that as, well, since by the definition of this inner product, okay. Now here I've associated the lambda with the a. I've associated the a with this, pj minus 1. But I don't have to do that. I can associate it with that instead. So really, it's the inner product. It's also the inner product of lambda pi pj minus 1. Now, here's the essential point. Pj minus 1 is orthogonal to all polynomials of lesser degree. Now, let's count degrees. This has degree j minus 1. This has degree I plus 1 because of the multiplication by lambda. I is ranging over all values from 0 to j minus 1. So, this is equal to 0 if I plus 1 is strictly less than j minus 1. In other words, I is less than j minus 2. So that means in that summation over there, all the terms are 0 except for the last 2. So now I can say that Gj, my new unnormalized orthogonal polynomial, is equal to lambda pj minus 1 minus the last term in the summation, so I equals j minus 1. So that'd be p j minus 1, whoops, lambda pj minus 1 times pj minus 1. And this coefficient, I'm going to call alpha j. And then I have one more term for I equal to j minus 2. So minus inner product of p I minus 2 lambda j minus 2 p j minus 1 p j minus 2. Okay. Now, called beta j minus 1. So in other words, alpha j is this inner product, and then beta j is this inner product. Okay. Although now what I'd like to do is get a simpler expression for beta j than the one I have here. So, okay. Make sure I have this right. Okay. I need to cheat for a second here. No, stop it. Okay. Oh. Okay. I'm going to move the lambda over to the other. This is I shifted it around here. I could shift it around here too. So, actually, yeah, I don't even need the other one. All right, so that's a little easier to work with. Because, notice that lambda pj minus 1 also appears up here. So this is equal to lambda pj minus 1 is equal to gj, and then these terms move to the other side. So plus alpha j pj minus 1 plus beta j minus 1 pj minus 2, and I still have this pj here. Now, pj is orthogonal to all polynomials of lesser degree. That includes this one and that one, degrees less than j. So I can cross these out. They don't contribute anything to the inner product. Now, gj now I have oh, okay. I have this over here. Gj I can write as, if I rearrange that equation over there, that's the same as inner product of gj of itself to the 1/2 times pj. Now, this is a constant. This, forgive me, inner product. That's a constant. I can pull that out. So, here's a lazy way to pull it out. Okay. What? Well, I had this inside here because the constant pulled out. Yeah, so you can always pull constants out of inner product. But the PJs are orthonormal. So the inner product of an orthonormal function or vector with itself is 1. So that's all I have. Okay, so I have this. So this equation and also this equation, I will need these two.
Is that still the 1/2?
Oh, I squared both sides. Because I've not squared here. I hate square roots. All right. I don't regret this, but any questions up to this point? Other questions?
Can you please explain how you cancel the pj minus 1?
Oh, YBs go away?
Yeah.
All right. Now I can break this up into multiple inner products. Alpha j and beta j minus 1 are constants. You pull them out. So we have inner product of pj with lower degree. All right. You have questions? Okay. Okay. Now that I have those recursion coefficients, formulas alpha j and beta j. Okay, so now I'm going to rewrite the recurrence relation because the key point is here, each new polynomial depends only on the previous two. So that's called a three-term recurrence relation. All orthogonal polynomials satisfy a three-term recurrence. That's one of the nice things about them. Makes it easier to generate. Okay, so Gj of lambda, which is the same as beta j pj, because of how I defined all these things, is equal to lambda minus alpha j, pj minus 1, minus beta j minus 1, pj minus 2. And what I did was, and what I wrote over here, I have two terms involving pj minus 1, so I combined them. In here. So, what I'm going to do now, with this recurrence relation that relates ordinary polynomials, functions of lambda, I want to get back to vectors, because that's what I really want. So I'm going to, for lambda, I'm going to plug in A. And then I'm going to multiply, then I'll have a matrix function. Then I'll multiply that by R1. So I have Gj of A, R1, which is the same as beta j, Pj of A, R1, which is equal to A minus alpha j identity, Pj minus 1 of A, R1, minus beta j minus 1, Pj minus 2 of A, R1. Okay. And the reason I'm doing that is now I can abbreviate some things in here. Because polynomials, the p's of A times R1, those are the q's, which we saw an eon ago, which is because I know that's how long this class feels to you. Okay. And this, I'm going to give this a name. I'm going to call it Vj. All right. So I have beta j, qj plus 1, which is equal to A minus alpha j identity qj minus beta j minus 1 qj minus 1. So now I have a three-term recurrence involving vectors instead of polynomials. So we can leave the polynomials behind now. Yay. All right. Now, we're not going to take this and rearrange it. So that's the same as saying A qj. So I take this term. And then you take everything else on this side. Who would the other side? So I have beta j minus 1, qj minus 1, plus alpha j qj, plus beta j qj plus 1. I'm forgetting about the VJ for now. Now, what this leads to is, okay. Yeah, it's going to be kind of cluttered, but, well, because here this applies to any J. So if I apply this to all, so this is for J equals 1 to up to K. So if I take AQ1, AQ2, etc., up to AQK, that gives me on the left side a capital QK. In other words, I have all those columns, and I slap them together into one matrix. And I have, what I have here, taking linear combinations of all the Qs. So I have QK times this matrix as alphas on the diagonal, betas above, betas below. And if you were to write out this in terms of the columns and carry out the matrix multiplication, you would recover exactly this in each column. It's going to be a big mess. But there's one term not accounted for by this, because QK has Q1, Q2, etc., up to Q, little qk. But I'm going to have this term also. So I have one last term that has beta k, little q, k plus 1. Okay, so then that's my freaky end of vector symbol. All right. Now, what if I took that equation, that matrix equation? Well, actually, I'm going to rewrite it. So I have AQK is equal to QK, well, this matrix again, alphas, betas, betas. All right, that thing. And then the last term, I can write it this way. It's actually, make sure I have this right. Okay. Oh, what I wrote there is wrong. Dang it. Okay. No, this is a matrix that can't have a single vector here. I could use it with a different relation. Okay. This only occurs in the last column. So I have a matrix, and beta k qk plus 1 is in the last column of this matrix. So that's the same. That's equivalent to saying I have beta k qk plus 1 ek transpose. It's an outer product. Ek is a vector that has all zeros. The 1 in the last position. That's why this guy's in the last column. Now, I'm going to take the inner product of both sides with qk, capital QK. So qk transpose AQK is qk transpose qk, dang it, times this freaky matrix with my alphas and betas that I'm too lazy to write. And then capital QK has the Q1 up to QK. That's orthogonal to this. So there is nothing else, 0. Now, we've seen this expression before. I gave it a name. What is it? Yes. What? What? No, go ahead and say it.
There's
No.
With the current
Q, A,
ODK?
Q, okay, hold on. Figure out what I wrote.
So I'm saving time. TK. Is that what you just found? Okay.
Oh, yeah.
Yeah. So
Yeah, it's right there.
So TK is this matrix. It has the alphas on the diagonal. Above and below, and betas above and below. So we saw the matrix TK before as a way to get the coefficients of your solution, YK. We knew back then the matrix was symmetric, positive, definite. Now we also know that it is tridiagonal. So systems involving this matrix are particularly easy to solve. Very efficient. It takes only order K operations. All right. Now, what's left? Oh, I'm not going to finish. Some things will have to wait for
Well,
Wednesday.
isn't that
What?
Isn't that TK on the right-hand side too?
Well, this? Yes. But this is identity.
Yeah.
Yeah, so really my whole point was showing TK really is this.
Okay.
Yeah.
Why do we have the plus zero again? I know you said
Oh.
they're orthogonal, blah, blah, blah.
All the columns of capital QK are orthogonal to this vector.
Okay.
Yeah, so capital QK transpose little qk plus 1 is the zero vector. So that's what causes that term to go away. All right. So what I can write down, okay, well, I'm not going to go through all the mechanics here, but you can use this, can show that the new residual, RK plus 1, which is B minus AXK, is parallel to, so it's a scalar multiple of QK plus 1. Because what I showed you earlier, which again feels like an eternity ago, that residual is equal to B minus AQKYK. Now, AQK I have this expression for. If I took this expression, dumped it in here, and keep in mind what YK is, a whole bunch of things would cancel out. And I have that done in a book, I just haven't been too lazy to write it here. But what you end up with is a multiple of little qk plus 1. So that shows each residual is orthogonal to all previous residuals. Or in other words, it confirms that, even though it's by design. Okay. So now that we have all these entities, we need an actual sensible algorithm that carries all this out in such a way that it actually produces the solution. And I'm not going to get to the most efficient form of that algorithm, but I can give you an algorithm, and then on Wednesday I can say, well, here's how we make it more efficient. But the thing is, we have just got to put all these pieces together. Or maybe I can. Let's see. All right. Well, all right, so this is a Lanczos algorithm. I'm going to actually write this kind of like from the bottom up. You'll see why in a second. So what I had before, I had this recurrence relation, BK is equal to AQK minus alpha KQK minus 1 QK minus 1. So we have this recurrence relation That was established earlier. Now, and the thing is, once we have the alphas and betas, we can construct our solution. Really, it's the alphas, the betas, and all the q's. Now, this is helping us get each new q, but the thing is, I need the alphas and betas. So you can think of, if you look at this here, this is the only line we have. What do we not know? We're given A. We don't know the q's. We don't know the alphas and betas either. So they're like prerequisites, if you will. So I need to fill in something for those so that the statement can be carried out. Now, alpha k, which I previously given as this inner product involving orthogonal polynomials. But that is R1 transpose Pj minus 1 of A transpose A Pj minus 1 of A R1. Just filling in what the inner product was, how I defined it earlier. But this is Qj. So it's actually Qj transpose A Qj. This is my Qj, the definition that I gave earlier. So now we have a nice simple expression. Oh, sorry. K, not J. Dang it. I gotta fix all these letters. I need to be on a tape delay for taking notes. All right. Now, what about the
So does that need to be QJ or QK?
Yes. All right. So now we have the alphas. What about the betas? Well, beta k is so the square root of the inner product of gk with itself. But if I do the same thing, fill in what it is in terms of the inner product, I get a vector again. I actually get the norm of vk, because vk is gk of A R1. So if I dump that, so if I express this inner product exactly like I did here, then I get square root of inner product of vk with itself, which is the norm. Okay, so now I have alphas and betas. Oh God. Okay. Also, once I have betas, I know how to get q's, because each q is equal to the previous v over previous beta. So, so I pretty much have all the essential steps of generating all the entities I need. It's just not in the form of a coherent program yet. So initially, I have beta naught is the norm of, well, okay. I compute R1. I can get that immediately from my initial guess. I can get beta naught as the norm of that. And from that, I can get, so if you want, you can think of R1 as being like V1. Actually, like V0. Okay. So if I carry out these up front, I can get my first Q. And from my Q, I can get alpha. Once I have alpha, and my previous Q's and betas, I get the next V. From each new V, I get the next beta. So it all goes around in a cycle. So I just have to write a coherent for loop that's going to carry out that iterative process. And it's something I'm not keen on rushing when I have 1 minute left. So the thing I want to take away from this board here is we now have good formulas for the alphas and the betas in terms of the vectors that we have. Again, we don't want to deal with those polynomials directly. We want to deal with vectors. And now we can do that. Here's the information that we're given at the outset. And we also have a way to get from all the previous Q's to the new Q. And we have the information, and from all this information, we can compute the solution to AX equals B, or at least each iterate towards it. So what I'll do at the start on Wednesday is take everything we know, all these relationships, and write code from it. Because that's really, we have all these things that have been set up mathematically. It's like, well, how do I make a procedure from that? And that's something I want to spend time on. So I'll do that Wednesday.